Dr. Trent Ford has been the Illinois State Climatologist since 2019. He and his team provide information online through traditional and social media and by speaking to interested groups across the state. In addition to his role in education and climate outreach, Ford also conducts research on the climate system and extreme climate events, like drought, of course, and heat waves. Studies climate change, and much more. He is a native of Roanoke, Illinois. Ford earned a BA in geography from the Illinois State University before completing his master's and PhD at Texas A&M. Let's welcome Dr. Trent Ford.
Okay, well, thank you very much, Rita and DeLoss. Thank you for the folks for inviting me up here today to talk about, I think Rita said interested groups. Interested or hostage groups, I think, is usually the people I talk about, especially when it comes to climate change. That's what I'm going to talk about today. Trying to talk about, originally I think my title included temperature, but I really only have enough time to talk about precipitation. So our changes in precipitation, what we're seeing here in Illinois over the last especially 70 to 100 years, what we think we're going to see over the next 100 years, and then kind of more specifically the implications of what that means for what everybody's in this room for, which is nutrient management. So this is kind of letting the cat out of the bag first. This is what climate change has looked like over the last 100 years or so, 120 years in Illinois. Broadly, it's warmer and it's wetter. Every season in Illinois and every county in Illinois has gotten warmer and wetter over the last 125 years. Winter has warmed at a faster rate than summer, interestingly enough, and spring and summer have increased in rainfall faster than fall and winter. But overall, this is the sort of trend. And the national reports that have to cover whole regions and whole states in a matter of just a few pages stop here. It's warmer, it's wetter, sort of figure out what that means for you, right? And usually that's insufficient to understand what these impacts are for insert thing here: conservation, wastewater management, in this case, nutrient loss reduction and management of nutrients. What does that actually mean? Here's what we're seeing as far as projections. This is from the recent Illinois Climate Assessment, and these are showing model projections by mid and end of century for temperature on the left and precipitation on the right. You can see reddish colors on the left maps. That's showing that models are fairly confident we're going to continue to see the warming trend we've seen over the last 100 years or so by the end of the century. And the greenish, bluish colors on the right-hand side map show that models are decently confident that we're going to continue to see the wetting trend as well. And so this is really just giving the idea that the patterns that we've seen, the changes we've seen over the last 100 years are not going away. Now, these are showing trends. And indeed, if I go back to my previous slide, we have a lot of year-to-year variability on top of that, which is extremely important. I just gave a talk yesterday about climate change and wetter overall conditions in northern Illinois, and that's an area that had pretty significant drought last year, right? And so this is a big important point. We can still have the variability on top of the longer-term trends. These are the longer-term trends, though. Great. So the big question is, again, insert sector here, what does this mean for nutrient management? What are the kind of the specifics as far as what we're looking at? So first and foremost, getting into more detail, I think probably the most important aspect of our change that we've seen recently is more intense rainfall. So it's not just we're getting more rainfall overall, but it's coming in shorter bursts, more intense rainfall overall, and this is disproportionately occurring in the spring and the summer. So heavy rainfall is becoming more frequent, especially in those two warm seasons. To give you an idea, statewide, the likelihood of getting 2 inches of rain in a single day has increased 40% in the last 50 years, a little bit more in northern Illinois, a little bit less in southern Illinois. So that's what we're seeing, that increase of those very heavy precipitation days, which in this case for us climatologists usually define as 2-inch rainfall events. Of course, we know impacts from this. We have crop inundation, standing water. I mean, I can put pretty much each of the last 3 years, depending on where you are in the state, 2019, 2020, here in central Illinois, 2021. Now in northern Illinois, maybe not the case, but you can see that photo there, taken in DeWitt County around Farmer City. That was from this last year, when we had in the Bloomington Normal to Gibson City area, anywhere from 8 to 10 inches of rain in about a few days. We also have, more relevant for this community, we have more runoff. The soil is only going to take in so much of that water. Even if that soil is very dry, has a lot of capacity to take in that water, it's only going to take in so much. And if we're getting more rainfall in shorter bursts, we're going to have more of that runoff. And of course, it's not just the runoff of water, as you all know better than I do, it's the runoff of things going along with the water, soil, nutrients in particular. We still have to get work done, despite the fact that soils are increasingly wet in the spring, which means that when a lot of that work gets done, we have issues with soil compaction, which then affects the hydrologic and hydraulic properties of that soil and can actually make it more likely that we're going to get even more runoff from that soil if there's damage along with that. And then, of course, there's things like delayed planting and harvest. My big spiel when I get up and talk to ag groups about what climate change means for ag in Illinois is that it just makes things harder. It does. It's not an apocalyptic thing like some reports would have you believe, but it just makes things harder. Shortens time windows. It compresses windows. And when people are trying to get 2 months worth of work done in 2 weeks, it can make for issues. It can make it hard to do proper management of things like nutrients. So that's another thing as well. And then, interestingly enough, kind of a paradoxic relationship here is that this increased runoff and overall higher intensity of rainfall can actually make us less resilient to drought, short-term dry spells. One example of this, just an extreme example, in 2020, in the summer, Peoria got 50% of its total summer rainfall in 6 hours. It was bone dry in June, got about 6.5 inches of rain. The city of Peoria had flooding along the Illinois, and along some creeks that flow into it, and then bone dry for the rest of July and August. Right? And so when you look at 2020, in the summer of 2020 in Peoria, it's actually wetter than normal. But of course, on the ground, that doesn't mean anything because we get that burst of rain, the vast majority of it runs off, and then not only do we have some flooding issues, flash flooding, urban flooding, as well as flooding from agricultural fields, but that water that we were supposed to get over 2 weeks is now all gone. You don't have anything in your soil. And so it actually increases the risk of short-term dry spells as well. And I mean, some of you have experienced these worse than I have, but just I update this set of events to show the sort of extreme rainfall events we've experienced in the last few years. So for example, I mean, this spans the state. We got January 2020 in Vandalia when the Kaskaskia River overtopped a few levees and caused some issues. One of the pictures down there on the bottom is showing the flooded Willis Tower basement, which we got 8 inches of rain in just 4 days in Chicago. And some folks had to make some pretty big decisions in a very short period of time to make sure that the whole downtown wasn't flooded with sewer water. Quincy had a significant rainfall event, and like I mentioned, in Peoria had a really bad rainfall event in July of 2020. And then just this last year, Bloomington Normal area, and it was even worse further south near Hayworth in McLean County, got over 10 inches of rain in 3 days, which is absolutely incredible. And then Gibson City said, hold my beer, I'm going to get 10 inches of rain in 6 hours. Right? That Gibson City event was something that I could probably go the rest of my career without ever seeing again. It was absolutely incredible in a terrible way. Storms just trained, and the estimates I'm going to show you in a little bit here when we talk about design storms, a 100-year storm, whatever, 500-year storm, that blew away the things we have. The National Weather Service put the estimate as like a 1,000-year storm in Gibson City, but we only have 120 years of record. We don't know what a 1,000-year storm looks like. That's just based on extrapolation of the curve. It's just amazing, that amount of intensity. So I am not up here saying that everybody's going to be like Gibson City in the next 10 years, right? Again, we can go the rest of the year, but these are just some of the extremes. But it's not just the extremes that are changing, it's the kind of nuisance storms as well. Now, scientists at the Water Survey and others at IDNR recognized this a few years ago, including my predecessor, Jim Angel. And so they said, well, hey, we need to update these design storm estimates, these estimates of the 100-year storm, for example, the one that has a 1% chance of happening any given year. You see Momchilo in the back there. He was one of the scientists that did this, so hopefully I can represent your work very well. And to make sure that the infrastructure we're building that has a 50 to 100-year lifetime is going to be applicable for the climate that it's going to experience. And so to put this graphically, what I'm showing you here in this plot, the dark lines, the solid lines are the new 2019 estimates of design storm precipitation totals. The dashed lines are over the same time period, the ones from 1989, from the original Bulletin 70. The different colors show the duration of the storm. So, for example, the blue line shows 6-hour totals of precipitation for a 6-hour storm. The red lines show a 1-day, 24-hour storm. The black lines show a 10-day storm. And then we have the different return intervals going from 1 year to 100-year return intervals. And you can see that for the vast, and this is for southwest Illinois, so you think like the St. Louis Metro East up to close to Quincy. So we can see that for almost every return period and for almost every duration of storm, the new estimates are significantly higher than the old estimates back in 1989. And to put some actual totals to this, so you don't have to squint at the graph here, for the 2-year return storm, that has a 50% chance of annual occurrence. It means a 50% chance of this storm happening any given year. The 1-day total for that storm is increased by 1/2 inch. So where it was 3.5 inches in southwest Illinois, now it's 4 inches. And as we know, we get that 24-hour total. That additional 1/2 inch can make a huge difference. It will go over a 24-hour period of time. The 10-day total for the 2-year storm increased by 1.25 inches. For a little bit more of extreme, a 10-year storm has a 10% chance of annual occurrence or annual exceedance. The 1-day total increased by almost 1/2 inch, the 10-day by almost 1.5 inches. And these aren't super extreme. This isn't a 100-year storm that we build retention basins and skyscrapers to. These are storms that we expect. Again, the 2-year storm is 50% chance of annual occurrence. So again, it's not just those extreme storms. I point to Gibson City and say, looky here, right? There's a really extreme event, but it's actually these nuisance storms that are changing as well. So what happens when we get intense precipitation? Well, a lot of it tends to run off. We get an increase in runoff. Now, these are back-of-the-envelope calculations done by a climatologist, so they will not scale to a 2,500-acre farm. But if we take, for example, a 10-acre plot of cultivated land, based on the 1989 estimates of a 5-year design storm, has a 20% chance of happening any given year, that's our peak and runoff volume for a 1-hour storm. It's 0.36 acre-feet. And again, there's some uncertainty about this because it was a climatologist that did it. But based on the 2019 estimates of that same storm, just with newer data, that increases to 0.42 acre-feet. And that's just from a 1-hour storm. So we're talking about without any change in land cover, without any change in management practices, without any change in anything except our weather and our climate, we have more runoff. And so you can kind of see where I may be going with this as it relates to nutrient management, right? When I talk about climate change and trying to set goals for things, I usually use the sports pun of like moving the goal line, right? To say like, okay, we're setting up for a 30-yard kick, and as soon as that snap is taken, that goalpost moves back 10 yards. And if you're not a football fan, I'm sorry, this is probably just not making any sense to you. Basically, it just makes it harder. What we plan for is constantly changing, right? And our plans are stationary, but our climate is just not. So that was kind of focusing on some of the shorter-term extremes. But, you know, we have to put that in the context of longer-term extremes as well. It's not just our 1-day, 10-day storms that are changing. We're getting wetter overall, and that's the important context. What these maps are showing from a recent study, looking at changes in kind of our annual maximum wetness or minimum wetness and mean wetness. You know, how wet are we getting at 1, 3, and 6-month time periods? Anywhere you see blue across the Midwest there, that's an area where we have a significant increase in overall wet conditions across the area at those time intervals. So all of Illinois and most of the Midwest has gotten wetter since the 1950s. That's kind of the middle panel there. That's what I showed you before with the first plot that I showed. But the top panels are showing the annual maximum wetness. And what that is showing is that our maximum wetness, how wet we're getting maximally in any given year, is increasing at a faster rate than our overall precipitation is. So if you think about a distribution of rainfall, climate change should take that distribution and just shift it. But it's not. It's actually changing the distribution so that our maximum values, our extreme values, are changing at a faster rate than our mean is, right? So again, that makes it harder to understand, to model what we're going to look like as far as runoff and stream flow and things like that. And the largest trends, interestingly enough, the darkest blues there are in our 6+ month totals. A lot more variability at the 30-day, the kind of 1-month totals. We have some dry, we have some wet. Overall, it's getting wetter, but we don't have stronger trends. It's the 6+ month totals that are increasing, which means that our background climate is getting wetter. We have much more extreme wetness at the 6+ month totals. All right, so over a 6-month time period, we're overall wetter. I'll talk about the impacts of that in just a second. Now, thinking about projections, These maps are similar. What they're showing is our projected changes by late century in our annual kind of maximum wetness. And from bottom to top, we're going higher emission scenarios, right? So how much carbon dioxide, how much greenhouse gases are emitted between now and the end of the century. By late century, precipitation is sensitive to that. By mid-century, we don't see a whole lot of sensitivity. But by late century, what we see here is that models project pretty much for all scenarios, for all of the Midwest in varying levels of intensity, continued precipitation increases at 1, 3, and 6-month totals. But you see the darkest color blue under the 6-month totals, which means the trends that we've seen over the last 50 years, the models not only pick those up fairly well, surprisingly well, actually, but they also project a continuation of that. And so, again, the largest changes in wetter conditions at 6+ months variability. At 1 month variability, some of the lighter shades of blue are because we have a lot of, at 1 month, we have a lot of variability. Shorter-term dry spells, pronounced wetness at 1 month lead to an overall decrease in the trend. So the impacts, what does this mean when it comes to nutrient management? It means that we're overall, our deeper layer soils, let's say 2-3 feet and below, our water tables and our stream for our base flow that determines stream levels, that is more sensitive to these longer-term changes in longer-term wetness, 6+ month wetness. The storms that I talked about, the Gibson City storm, our 2-year storm that I talked about with runoff, that's more affecting our topsoil. But our deeper layer soil kind of sets the tone for longer time periods, and it's more responsive to those 6+ month totals, out to a year, if not a year and a half. Right? And so what that means is that having those wetter soils, having those higher water tables, because we have this overall background wetting, means that we have a higher runoff potential because the water that we do get in the topsoil can't drain as effectively. Something that we saw this year, I bought a house in early 2020 in the Champaign area, and from October of last year until just a few weeks ago, I had some standing water in my backyard, and I tried over and over, what's going on, is it a sump pump, what's going on? It ended up being that the groundwater was right here, off the surface. It just has started to drop a little bit, but that's kind of what we're seeing. And when that happens, it doesn't matter if you only get 1/10 of an inch of rain, the water has nowhere to go. So you have a more runoff potential. More frequently, excessively wet soils as well, complicating management. It makes it harder to do things when the spring is so stinking wet. And then there's a little bit of drought resistance that can come from this, but a little bit less relevant for nutrient runoff or nutrient reductions. Okay, so last kind of bit I want to talk about that I haven't really hit on yet is a change in seasonality. When this happens matters just as much as if it's happening at all. And so models projecting what we've seen, as I mentioned before, wetter springs overall. Models are projecting springs to become even wetter, that kind of continuation of that trend. The maps on the right-hand side are also from our recent Illinois climate assessment, showing kind of the seasonality of precipitation changes over Illinois. And what we see is that spring and winter, those darker shades of blue are projected to become even wetter. Now, the sort of drier colors in summer, I think those are overblown. We have a lot of uncertainty when it comes to summer precipitation. One thing that we do know is that summer precipitation is becoming more variable, kind of like I mentioned with Peoria getting half their summer rain in 6 hours, right? But taking the spring alone, with disregarding what's happening in the summer, it means that wet springs like 2019 become more frequent. We just finished a paper that we saw where the state-of-the-art climate projections show springs like 2019 across the Midwest have a return period of 1 in 5 years by late century. 1 in 5 years for a year like 2019, right? We know what that looks like. We can see there from that image from Bureau County where we just couldn't plant that field that year. Some folks tried to mud it in late June. So this is something that we're going to be dealing with even more. Now, again, sometimes I can be a real gloomy Gus, which is why I said hold audiences hostage. This isn't something that's going to be entirely, I guess, like apocalyptic kind of thing where climate change is unavoidable and all of that sort of thing. But what this does is it just makes management that much harder. It just makes management that much more necessary, I should say. So last slide here is a summary. The top summary here, we've gotten wetter. It's very likely we're going to continue to get wetter. Those sorts of trends, if we can believe the models, which we can because they have a good amount of certainty in spring precipitation, the trends that we're seeing are likely to continue. This isn't going away. And again, especially in problems in winter and spring. More frequent heavy precipitation just kind of exacerbates those issues with runoff. I use this Venn diagram here. I borrowed this from talks to hazard mitigation planning when you think about your assets and your hazards. And I want to use this, and it may be an imperfect analogy here, but I kind of want to use it. So we have things that are causing, we think, the risk of nutrient loss. The risk overall of nutrient loss is largely defined by two things: the weather, right? How much extremes we're getting, the location of the extreme, the severity extreme, yada, yada, and then the planning, the kind of action, right? Your soil health, your water management, your nutrient management, your land use, the policy, the funding that goes into these problems, right? All of those combine to give you your overall risk. Climate change is an externality for any economists that are in the room, right? Climate change is acting on extreme weather. It's just making those extremes more and more frequent. And so what that does is it increases your risk even in the face of better management and planning. So that's kind of the last summary here, is that climate change, it's not this kind of enigma that it can kind of be painted in the media especially, but it's something that's a management issue. It exacerbates nutrient loss issues and can offset improved nutrient management. It can make it just harder, as we've seen. I take that quote from the 2021 biennial report. Further efforts are required. We need more to achieve these goals that we want, the 15% reduction, let's say, because our climate conditions are working against us. Our goalpost is moving. So what that means, it makes reduction strategies, it makes actions on the ground, policies, funding, resources, it can all just be chalked up to resources, that much more important to implement because our climate's working against us. And so the last point here, management plans have to account for those changing precipitation patterns, both present and future, to understand where we're at and the likelihood of meeting those goals. And I should say, I'm not advocating to say, well, we said a 15% reduction by 2025, but the climate's working against us, let's knock that down to 10%. No. 15% is a good number. That's what the council came up with, and it's scientifically sound, but it's going to take that much more resources to get there because our climate's working against us. So with that, my contact information is below. I'm happy to hear from anybody who has issues, thoughts, wants data, information on these things. And with that, if there's time left, I'm happy to take any questions. Okay, good.
So my question is, are there multiple models that point in a similar direction? And if not, how widely do those different models vary in their predictions of the future?
Yeah, so the weather prediction is actually quite a bit different beast than climate prediction, just because weather prediction is almost entirely based on physics. So I think Rita and DeLoss mentioned the weather coming in this next few days. We can't really nail down who's going to get snow versus freezing rain up till a few hours out. That's completely separate than climate prediction because the climate works off of different mechanisms that are, in some cases, even more predictable. What I'm showing, my interpretation of the model output is based off of the sign of the model change and the agreement between many models. So the worst thing a climatologist can do, other than miscommunicate things, is run one model and then call her quits. And so what the results that I showed, all of those results are based off of at least 20, if not closer to 100 different simulations from either a single model with different ensemble runs or multiple models. Now I mentioned I kind of downplayed that dryness signal in summertime. The reason I downplayed it is because the models are all over the place. Whereas for spring, all of the models point to changes. Now the degree of that change varies, which is why we show the kind of the multi-model mean, the kind of cone of uncertainty. But the things that I talk about when I talk about the interpretation of spring changes, those temperature changes, the confidence in the models, that's based off of the agreement between those. Really good question.
Trent, thanks for a great presentation. Can you speak to the global factors that are driving the increase in precipitation, i.e. why? Why is this happening?
Yeah, it's a good question. So, this is how when we get those IPCC reports, the Intergovernmental Panel on Climate Change, they tend to focus on global regions, and it's hard to understand what that means for us. So the change in our climate, the thing that we can define as climate change, the warmer, wetter that I talked about, that is directly linked to the increase in greenhouse gas concentrations in the atmosphere, Carbon dioxide drives the bus. Methane plays an important role, as do a few other greenhouse gases. We've seen that marked increase in carbon dioxide concentrations, especially over the last 50 to 70 years, really going back close to 100 years now. That is directly due to human activity, basically just energy creation. So that's what's really driving the bus at the global scale. Now, the reason that it's called we have global warming. That's basically what that refers to. Higher greenhouse gases in the atmosphere, warmer planet overall. But the reason we really focus on climate change instead of global warming is because the climate system is pretty complex, meaning that different climates are going to change in a different way. So, for example, if you're looking at the desert Southwest, they're looking at a drying trend that's pretty significant. There was a paper just published a couple days ago showing that 1,200-year mega drought, or the worst in the West. And whereas the biggest, I think the most significant change we've seen as a result of those global forces here in the Midwest, and the models showing that agreement are likely to see into the future is that wetting trend. So that's sort of how we link to the global. Now, I guess taking this to the next step, we talk about mitigation. All right, I kind of focus a lot of my talk on adaptation because that's really a lot of what we can do here at the state level. But at the global level, mitigation means reducing, eliminating those greenhouse gas emissions and reducing concentrations or stabilizing concentrations. And the faster that happens at the global level, the less the impacts are here at the local level, if that makes sense. So that's how that connection is. Now, I mentioned precipitation changes by mid-century, 30 years from now, which is just amazing that we're there, less than 30 years. That is less sensitive to that mitigation at the global level than changes by late century, because we have a lag effect. The kind of extremes that we're seeing now are really the result of actions that were taken, 30, 50, 70 years ago. So if we were to eliminate all CO2 emissions now, today, we would still see some of these changes by mid-century. By late century is where we really see those begin to drop off. So when I talk about the impacts related to that, it's really those late century impacts that are really responsive to mitigation, which is why I don't pluck the string of mitigation so much in talks like this, because we're looking at 20 years, right? We got to do something about 3 years, right? 2025 is the and so it's really more about adaptation to here's what we're seeing as far as these changes are concerned. Hopefully that answers the question.
I only ask a lot of questions as I'm trying to understand. I'm not picking on you or anything like that. Don't take it that way. I just have a lot of questions about model prediction and what all that they try to understand, right? I mean, you know this way better than I, but if we do get more rainfall, what kind of other feedback loops does that create? So in other words, if we get more rainfall, carbon dioxide increases in the atmosphere, that would stimulate C3 plant development in a big way, which would take carbon out of the atmosphere. It's a very complex system. Are these models trying to take into account these feedback mechanisms? And again, I'm only trying to understand what they do and don't account for.
Yeah, no, it's good. This is why they used to be called global climate models, GCMs, and we try to move away from that to talk about Earth systems models, because I'm not an atmospheric scientist. I am a geographer, and I say that because I can make fun of atmospheric scientists then. But the atmospheric scientists were really the ones who developed the climate models first, and they really drove the bus, which means that early climate models were almost basically just simple atmospheric models. Then, probably 20, 30 years ago, depending on who you talk to, they started discovering, hey, we need the ocean folks and the land folks like myself and the ag folks and the urban folks to start doing this properly. And so the Earth systems models have really come a long way in the last 20 years at trying to capture those feedbacks. Now, as you mentioned, there are global scale feedbacks, the ice albedo feedback that makes the Arctic warm faster than all other regions. There's local feedbacks too that are really important. So an Earth system model can capture the ice albedo feedback for the Arctic. Can it capture feedback from wide-scale irrigation, cropland irrigation in eastern Nebraska? That's a good question, which is why a lot of times when we focus on modeling of climate change at the regional scale, we'll look to take the big, complex Earth systems models and push them into a regional model where we can tweak some of those feedbacks. Because what's happening in the desert Southwest or in mainland China or wherever. The South Pacific is very different than what's happening here in the Midwest, and so that's kind of where that regional focus goes. So they do get those feedbacks. The degree of skill is still variable between models, but they do capture those. They're trying to capture those all the time. And there's constant improvements. And this is one of the big things, is that's why looking at one model run and just saying, hey, there it is really, really problematic. But when you're seeing 30, 50 model runs, they're pointing in the same direction, we can say, okay, there's good amount of confidence. I just made the roof come down there. The confidence grows with those projections. Yeah.
And I just asked so many questions about the models because, we're going to spend lots of money and lots of time and lots of blood and treasure on planning. So we need to be confident that they're somewhat accurate. So that's why I asked so many questions.
Yeah,
Thank
no,
you.
this is a big thing, is that there's varying levels of confidence. And again, this is hard because I think the biennial report mentioned the period of 2015 through 2019 was extremely wet. It was. And it is more likely than not that 2020 through 2024 is not going to be as wet as 2015 to 2019, because there's year to year and decade to decade variability. And so that always has to be accounted for. It's just the background statistics of understanding, okay, here's what we're looking at as far as the long-term trend. And here are the things that are going to become more common, not every year, maybe not every 5 years, but more common as we move into the future. So that's, as I mentioned, the communication of climate change is arguably as important as the model projections themselves. Yeah.
I'm less interested in what's going to happen in 50 years. I'm more interested in the next 5 years, like you said, and what's happened in the last 20. So real quick, in the time we had left, I wonder if you could comment, because I was really interested in what you said about what's happening with precipitation events, the extremes changing more quickly than the mean. Groundwater levels, surface soil moisture content, and soil temperature. Just real quick, specifically that soil temperature component, what's happened in the last 20 years there?
Yeah, I cut off the temperature part, and I shouldn't have done that because I ran short. So what we're seeing overall is warming temperatures in the air are translating to warmer soil temperatures overall, but there's a seasonal component to it that's really important. Fall soil temperatures over the last 30 to 50 years have increased at a much larger rate than spring soil temperatures have, and that's all across the state. Fall, and I've heard this from a lot of folks on the ground, that the kind of edge of fall months like September and early October are acting more like summer months than fall months used to. And so we're seeing those extension of those warm soil temperatures. Now what happened this last year in October was a bit of an anomaly where we were 10 degrees above normal. We didn't hit 50 degrees even in northern Illinois until early November. But that's what we're seeing overall, those long-term soil temperature trends. Now, it is likely, with the projections of continued warming in the winter, in the spring, in the fall, that we will see an extension of those growing season soil temperatures both in the spring and in the fall. And that's kind of what we're looking at in the next 30 to 50 years, is that air temperatures translating to those soil temperatures as well. So taking longer to cool down in the fall, warming up a bit faster in the spring. One of the implications of that, like I mentioned, I cut out from the slide of warmer fall temperatures, is it pushes back timelines for example, fall nitrogen fertilizer application. And as we know, our winter months are warming, but winter is a lot more variable than fall is as far as weather is concerned. We can usually bank on a good 10 to 14 days in the fall of pretty dry, seasonably cooler conditions. In the winter, it's all over the place, and so pushing those soil temperature thresholds later into the fall and early winter becomes an issue with again, just application management issues, things like that. So that is what we're seeing with soil temperatures.
I guess we're lucky in that we're wetter instead of drier. But with that, we've put on a lot of nitrogen in the fall. Have there been any models that have looked at how the warmer temperatures and the wetter springs are going to influence nitrogen loss out of our current production system?
I don't think I don't think I can adequately answer that question. There may be people in the room who either are doing that research and would love to talk to you about it, or can point to better research. I'm not aware of that, but it certainly doesn't mean it doesn't exist.